This tar looks pretty solid, but actually it is liquid, a very viscous liquid. The brick has barely moved, but if we were to come back in a few days and cut open this barrel of tar, we would find the brick at the bottom. There are two kinds of forces having to do with the motion of the tar as it is pushed aside by the brick. First, the viscous shear stresses resisting the deformation of the tar particles. Second, what we might call the inertial resistance to acceleration of the tar particles. Just looking at it, though, we can see that the acceleration of any tar particle is exceedingly small. The viscous resistance to deformation, on the other hand, is obviously extraordinarily large. Compared with the inertial forces, the viscous forces seem almost infinite. You will remember that the motion of each fluid particle is governed by Newton's law, involving a balance among several forces. Now, under what conditions will it be possible to neglect the inertial forces in this balance? Let us recall that the Reynolds number is a measure of the ratio of the inertial forces to the viscous forces. As the Reynolds number decreases, the inertial forces become relatively less important compared with the viscous forces. In the limiting case of extremely small Reynolds number, the inertial forces are virtually negligible, and there is, for all practical purposes, a balance between the pressure forces and the viscous forces only. Let's look at an example. In this pan of very viscous glycerin, we have marked with dye squares of liquid, so that we may see the motion of the fluid as I push this cylinder through it. You can see the fluid particles deform as they flow past the cylinder. The motions are so very slow that hardly any acceleration of the fluid is involved. But these slow deformations lead to very large viscous forces because the fluid is very viscous. Now, it is a remarkable fact that the flow may behave in a very viscous way, even though the fluid has only a small viscosity. Let us see why. If we look at the expression for the Reynolds number, we see that there appears not only the viscosity of the fluid, but also the density of the fluid, and the speed of the flow, and the size of the object. From the algebraic arrangement of the Reynolds number, we see that a very large viscosity leads to a very low Reynolds number, and thus to a flow dominated by viscous forces. But we can also see that low Reynolds number may be had in other ways. For instance, a very low density has the same effect on Reynolds number as a very high viscosity. So flight through rarefied air at very high altitudes may represent a very viscous flow, even though in ordinary language we would describe the rarefied air as thin. Other examples of flows dominated by viscous forces, that is, with low Reynolds number, are those with very low speeds or very small sizes. For example, if a sufficiently small object moves sufficiently slowly through air, the flow is very viscous, even though air has only a small viscosity. This is just what happens when a speck of dust settles slowly in a room. The viscous forces are relatively stronger for the tiny dust particles settling through air than they are for a large steel ball dropping through a column of highly viscous glycerin. From this point of view, it is more meaningful to speak of a very viscous situation than of a very viscous fluid. About 100 years ago, Sir George Stokes, by using the postulate that inertial forces are completely negligible, was able to derive mathematically a simple formula for the drag of an object at very low Reynolds number. According to Stokes's formula, the drag is directly proportional to the speed of the flow, to the viscosity of the fluid, and to the size of the object. The constant of proportionality is a pure number whose value depends only on the shape of the object. Now, logical as it may seem to be, the postulate that inertial forces are entirely negligible at low Reynolds number is so sweeping an assumption that one should not accept it without some experimental verification. To test the formula, we may choose a particular geometrical shape and carry out systematically a series of experiments in which we measure the drag, the speed, the viscosity, and the size. Then we can see whether these four quantities fit together in the form required by Stokes's law. And this, in turn, will be a test of whether the inertial forces can indeed be neglected at very low Reynolds number. The size of our objects we measure directly, the viscosity by a viscometer. Our particular experiments are falling body experiments, in which the speed is measured by the time required for the body to fall through a specified distance, and the drag is found from the net weight of the object in the liquid we use. If any three of the five quantities in this expression are kept unchanged, then the remaining two should be related by a simple proportionality. For instance, suppose that the distance, the viscosity, and the size are all unchanged. Then the drag should be inversely proportional to the time. That is, the product of the drag with the time should be constant. Or, if the drag, the distance, and the viscosity are all unchanged, then the ratio should be constant. As a third possibility, suppose that the drag, the distance, and the size are all unchanged. Then the ratio of the viscosity to the time should be constant. Here is our timer. We read seconds on the middle scale, hundredths of a second on the outer scale. There, just 6.11 seconds have elapsed. We have marked this column of liquid with two strings, exactly 10 centimeters apart. Here are the several objects for our experiments, all the same shape, all spheres. For our first set of experiments, we want everything unchanged but the drag. And so we have made these two spheres so that they have exactly the same diameter, but different net weights in glycerin. Let's drop the lighter one first. You see that the ball has reached terminal speed well before it reaches the first string. There. Now let's remember that at terminal speed, the net force in a body is 0. And so the drag on this ball is exactly equal to its net weight in glycerin. There, 20.02 seconds. Now for the heavier ball. This one weighs 4 times as much as the first in glycerin, and so it has 4 times as much drag. Start. Stop. Our reading is 4.91 seconds. Let's put these numbers into our table. If we call the drag of the light ball 1 unit, then the drag of the heavy ball is 4 units. The time of drop for the light ball was 20.02 seconds. Let's round it off to 20.0. For the heavy ball, the time of drop was 4.9. Multiply through 20.0, 19.6. According to Stokes, these numbers should be the same, and within experimental error, they are the same. And so we have one experimental verification of Stokes' law of drag. For the second test of Stokes' law of drag, we would like everything unchanged but the size. And so we have used these two spheres, which have exactly the same net weight in glycerin, and thus the same drag. The diameters of the two spheres are in the ratio of 1 to 2. For the same distance of fall, the times were 20.0 seconds and 38.6 seconds. Carrying out the divisions, we get 0.050 and 0.052. Allowing again for experimental error, these are the same. And so we have a second experimental verification of Stokes' law. For the third check of Stokes' law, we would like the only variable to be the viscosity. Here is the apparatus. Glycerin in this graduate, silicone oil in this one. The silicone oil is even more viscous than the glycerin, 61 times as viscous. And here are the spheres, all having the same diameter, and all having the same net weights when immersed in the appropriate liquid. The distance over which we measure the time of fall was 12 centimeters. With a viscometer, we measured the viscosities. For the glycerin, 1,000 units. For the silicone oil, 61,000 units. The times of fall were 4.12 seconds and 245 seconds. All this worked out as 242 and 249. Good agreement, considering the experimental errors. Well, now we have varied the size, the viscosity, and the drag. And we have seen that they affect the speed in just the way required by Stokes' law. But isn't it odd that the density of the fluid does not seem in any way to affect the drag? One might have thought that a heavy fluid would offer more resistance than a lighter fluid. Perhaps we'd better look into this. These two tubes now contain air. In this one, at ordinary atmospheric pressure. 99% of the air has been evacuated from the second tube. So the air density in the second tube is only 1% of the air density in the first tube. We are going to release very small dust particles from containers at the tops of the two tubes. Now, a remarkable thing about gases is that a large change in pressure does not change the viscosity, provided that the temperature remains the same. So the air in both tubes has the same viscosity, even though the densities differ by 100-fold. To our surprise, the terminal speeds are just the same. The rarefied air offers just as much resistance to the falling dust as the ordinary air. So Stokes's formula is correct, not only in the quantities it includes, but in what it excludes. These experiments, and many others of different type, give conclusive evidence that Stokes was right, that inertial forces are negligible at sufficiently low Reynolds numbers. Our last experiment is particularly impressive, for if inertial forces are unimportant, then the fluid density, which is after all only a measure of the fluid inertia, should be an irrelevant property, and we have seen that it is. We have discussed here what happens at very low Reynolds numbers. Forces are predominant. Now we turn to the other extreme, very high Reynolds number, where the viscous forces are very small compared with the inertial forces. For our high Reynolds numbers, we'll go to the wind tunnel room. To begin with, we shall make quantitative measurements to see how the drag of a good aerodynamic shape, such as this bomb, varies with the speed. I'm going to raise the speed first to 75 miles per hour. Then I will double it to 150 miles per hour. Then I will triple it to 225 miles per hour, each time measuring and recording the drag. You might notice, however, that as the drag force increases, the bomb lifts out of the jet. It is important that we make all the measurements with the bomb in exactly the same position relative to the air jet. Therefore, we have mounted the spring scale with a turnbuckle so that we may raise and lower the scale as a whole, in that way changing the position of the balance arm. The marker at the end of the balance arm tells us when the arm is in its standard position. All right, we're ready to go now. Now that we have these data, what can we make of them? Well, the first thing we notice is that when the speed was doubled, the drag force went up by more than a factor of 2. In fact, it went up by exactly a factor of 4. Then, when we tripled the speed, the drag force went up by much more than a factor of 3. In fact, by a factor of between 9 and 10. Is there any pattern to be seen in this? There is. If you made the guess that the drag force went as the square of the speed, you would be very nearly right. You see, 2 squared is 4, and 3 squared is 9, which is very close to the measurement of 9.5. And so it is a good approximate rule that in a slightly viscous flow, the drag force varies as the square of the speed. To get a complete picture of the law of drag for high Reynolds number, we would have to look into the effects of viscosity and density and size, as well as the effective speed. As a matter of fact, though, there is no simple and precise law of drag for high Reynolds number. For streamlined bodies, however, there is an approximate law of drag, which says that the drag is proportional to the square of the speed, to the density, and to the square of the size. Let's compare this approximate law for high Reynolds number with Stokes's law of drag for a very low Reynolds number. At low Reynolds number, doubling the speed doubles the drag. At high Reynolds number, doubling the speed quadruples the drag. At low Reynolds number, doubling the size doubles the drag. At high Reynolds number, doubling the size quadruples the drag. In the development of these laws of drag, a basic premise was that we deal with geometrically similar shapes, even though the size, the speed, and other factors could vary tremendously. When we first thought about the Reynolds number, we considered geometrically similar shapes. Remember also the plastic ball falling in water, and the helium-filled balloon rising in air. These experiments helped us to understand the idea of the Reynolds number as the key to dynamical similarity. Now we can carry this idea further. It can be shown that when experiments are carried out on geometrically similar shapes at the same Reynolds numbers, then the drag forces on the objects are related in a very special way. The drag force on the plastic ball falling at terminal speed is its net weight in water. We measured this. It was 0.020 grams. The drag force on the helium-filled balloon at terminal speed is the net buoyant force with which it tugs upward on a scale. We measured this. It was 0.0067 grams. These forces are quite different, but the principle of dynamical similarity tells us that if the Reynolds numbers are the same, then the so-called drag coefficients are the same. As you see, the drag coefficient is found by dividing the actual drag force by the square of the speed, by the density, and by the square of the size. Here in our table, we have all the numbers we need to calculate the drag coefficients for the two experiments. For the helium balloon rising in air, it came out to be 0.4019. For the plastic ball falling in water, it came out to be 0.4018. These are almost exactly the same, thus confirming that equality of Reynolds number leads to equality of drag coefficients. All this has the most profound implications. If you think about it for a moment, you will realize that once you know about the principle of dynamical similarity, you can predict the drag of the plastic ball falling in water. By measuring the forces on a scale model in a wind tunnel, we can predict the drag on the full-scale airplane at an altitude of 30,000 feet. Model testing and the principle of dynamical similarity are of great importance to aeronautical engineers designing airplanes, to naval architects designing ships, to civil engineers designing harbors, and to many other forms of engineering activity. With these laws of drag, and with the law of dynamic similitude connecting drag coefficient to Reynolds number, we are beginning to get a pretty good picture of drag in fluids. But much still remains unexplained. Suppose that we had a magical fluid, completely without viscosity, then it would offer no resistance at all. then why should fluids of extremely small viscosity produce as much drag as they do? And if they do, shouldn't viscosity enter into the law of drag for high Reynolds number? By rights, it should. Remember, this is an approximate drag law. There is an effect of viscosity, but often it is small enough to neglect for a broad picture. For example, doubling the viscosity increases the drag of a streamlined shape by only about 15%, which is relatively small. But for an unstreamlined object, like this ball, the effects of viscosity may be larger. And the peculiar drag speed curve we obtained in the wind tunnel suggests that they may be complicated too. No, viscosity cannot be neglected at very high Reynolds numbers. Viscosity is responsible for drag in the first place, and even the tiniest amount of viscosity may sometimes lead, indirectly, to a very large drag. And viscosity is the reason why shapes, which differ only slightly, may have very different drags. Now we must see why. Let us imagine that this is a flow of very small viscosity in which we have an airfoil. These wires represent trajectories of typical fluid particles. We call them streamlines. Now it is vital to understand that no matter how small the viscous forces may be throughout most of the flow, there are certain regions where they are exceedingly important. Basically, the reason is that in all fluids, the fluid particles immediately adjacent to solid boundaries do not slip relative to the boundary. Here is an apparatus which demonstrates this point. We are going to produce a flow of glycerin from this settling basin through the channel when we raise the gate at the end. With this marking pen, I lay down a thread of colored glycerin which will identify a line of fluid particles. Now, up with the gate. You can see that the fluid particles move fastest at the center of the channel, and that the fluid particles at the wall do not move at all. With this U-shaped line of glycerin, you can see that none of the particles next to the wall move relative to the wall. There is no slip. The motion of this line of particles shows that all the fluid particles at some distance from the wall move downstream with the same speed. Let's look at this again with the image in negative. In the time that has elapsed up to this point, the distance moved by each particle from its initial position is a measure of the average speed of that particle. Remembering that the arrows are proportional to particle speed, we see that there is a region of velocity defect between the motionless particles at the wall and the particles moving with full speed at some distance from the wall. This region of retarded flow is called a boundary layer because it occurs adjacent to solid boundaries. The formation of the boundary layer is initiated by the motionless layer of fluid right at the wall. This motionless layer exerts a viscous drag on the layer of fluid next to it, thus gradually slowing down that second layer. As the second layer loses momentum, it begins to exert a drag on a third layer, and so the third layer begins to lose momentum, and so on, from layer to layer. Thus, the decrease of velocity at the wall is diffused by viscosity outward through the fluid, and more fluid becomes caught up in the viscous boundary layer. The amount by which the boundary layer grows in a certain time or a certain distance depends on such things as the speed, the viscosity, and the density. In this experiment with a certain speed and viscosity, the boundary layer reached almost to mid-channel at the end of the run. Now, when we decrease the viscosity, the boundary layer grows less rapidly. Next, with the reduced viscosity, we'll increase the speed. The boundary layer grows less rapidly still, and is quite thin at the end of the run. Let's think of this now in terms of Reynolds number. When we decrease the viscosity, and also when we increase the velocity, the Reynolds number became larger. So we may generalize our observations by concluding that as the Reynolds number increases, the boundary layer becomes thinner and thinner. But no matter how large the Reynolds number, that is, no matter how small the viscosity, the viscous boundary layer never disappears, because the velocity at the wall remains zero. The Reynolds number for an airplane wing is so large that the boundary layer is only about as thick as this piece of plastic. Although the viscosity of air is very small, the viscous forces in this layer are considerable, because the velocity increases from 0 to hundreds of miles per hour in a distance of only about 1 millimeter. At the beach on a windy day, you lie down to get out of the wind. You are then deep in a boundary layer, where the airspeed is low. There is another aspect of fluid flow that is significant to boundary layers. Sometimes the flow seems very smooth. We call it laminar. At other times it is erratic and irregular. We call it turbulent. If a lighted cigarette lies in an ashtray in a very quiet room, one sees a wisp of smoke curling upward, smoothly, and without mixing. But at some point, it breaks up and diffuses irregularly and rapidly into the surrounding air. I'm going to do a similar but controllable experiment with this smoke generator. At low speed, at the point of transition from laminar to turbulent flow has occurred sooner. Low speed, high speed, low speed, high speed. Another familiar example is water running out of a faucet. At low speed, the surface of the jet is smooth and glassy. At high speed, rough and turbulent. Now, what is the essential difference between laminar and turbulent flows? It is this. In a laminar flow, the fluid particles move downstream on smooth trajectories without appreciable mixing between different layers of fluid. The flow is truly a steady one. In a turbulent flow, on the other hand, there is superposed on the average motion of the fluid an irregular and seemingly chaotic motion, which involves a great deal of mixing between different streamlines. This mixing, of course, exchanges fluid between different streamlines. But from a dynamical point of view, what is really important about the mixing, as we shall see later, is that it exchanges momentum between different layers. We should note also that the way we went from laminar to turbulent flow was by an increase in the speed of the smoke jet or the water jet. In other words, we increased the Reynolds number. In fact, it is usually true that at a low Reynolds number, the flow stays laminar, as we see here in glycerin. While at high Reynolds number, the flow is unstable and becomes turbulent, as we see here in water. By now you should be convinced that the Reynolds number is a remarkable organizing idea. It relates many different flows dynamically, if only they have geometrically similar boundaries. At one extreme, very low Reynolds number, we have demonstrated that the inertial forces are altogether negligible. This led us to Stokes's law as an accurate means for predicting drag, and to the surprising result that the drag is independent of the density. At the other extreme, very high Reynolds number, matters are not so simple. While viscosity is then unimportant throughout most of the flow, there are narrow regions near solid surfaces, boundary layers, where the viscous forces can never be neglected. We have seen, too, that the Reynolds number controls whether the flow has the steady, regular character we call laminar, or the unsteady, irregular character we call turbulent. The boundary layer and its laminar or turbulent behavior will figure crucially in our further explorations of the fluid dynamics of drag.